Hi, good afternoon, everyone, and thank you for taking your time to attend our Knowledge Series webinar organized by Genesis Ray. And we are just waiting for a few more people to join us. With me is Jack Huang, who will be also co-hosting this webinar with me. We've started this Knowledge Series webinar about a month ago. We had our first one on the 3rd of November. And that was on project site viability. So today, Jake will be introducing you to our speaker and also our panelists. So just let's take a look at the number of participants who has joined us. So we have close to about 70 people who have registered for this webinar. So just give us about a minute to get the others to join in. How's everyone? So you can see the panelists, but you're not able to see yourself. Don't worry, you are here with us as long as you can hear my voice and also Jake's. You will also get to hear later from the other panelists. Okay. Right. Without further ado, let me just introduce to you, let me just share with you my screen. Apologies for that. Okay. So, so this is the second of our Knowledge Series webinar, and you have just signed up for this. We really am honored, and we thank you so much for your willingness to spend an hour of your time with us. So I think let's begin with Jake, if you'd like to introduce a little bit about Genesis Ray and also on the speaker and our panelists. Please go ahead.
Okay, sure. Thank you, Rahima. And thank you everyone for being here with us this afternoon. As a technology company that provides solutions to the renewable and clean energy sector, we hope to embark on this journey with you, not only to create great solutions that are needed by the clean energy business, but also to share the knowledge of our expertise. We believe that sharing our knowledge will help create a better future for everyone who is involved in these exciting times to solve the world's need for a more sustainable form of clean energy. Now, please allow me to introduce to you our speaker and panelists. Today, for our main speaker, we have Dr. Abhishek Mishra, who is at present working as a senior analyst in our climate modeling team. His expertise lies in the area of climate modeling and handling large-scale data sets to help our GIS team in accurate resource mapping. Joining Dr. Abhishek are three other panelists, Vishnu Kunikrishnan, who leads our product development team, Dr. Pata Das, our power modeler, and Dr. Anushika Bose, our product innovation manager. Vishnu is heading the development of Genesis Ray's analytical products across the power and LNG sectors. His team's recent accomplishment is in the development of our GIS-based infrastructure mapping and analytics tool called GenRay Explorer. Next, we have Dr. Pata Das, who is currently involved in building optimization models, data wrangling, and visualization related to the power system operation and planning. Lastly, we have Dr. Anushika Bose, our product innovation manager, who is also our renewables geospatial expert. Her past work includes her stint as an environmental scientist at the Helmholtz Environmental Research Center in Germany. During the presentation, Your microphone will be muted throughout. However, you are able to post questions in the Q&A and chat box. One of our panelists will help you answer the question either in private or will take it over towards the end of the webinar. I now hand over the session to Dr. Abhishek to spend a good 25 minutes with you. Dr. Abhishek, please.
Yep. Thank you so much, Jake. So I'll just share my screen. Oops. Yeah, so I'll just beg you an apology. I'll just switch off my video, mainly because of the internet speed. It might disrupt the connection in between. So apology for that. Okay. So thanks, Rahima. Thanks, Jake. And welcome everyone to the webinar. Uh, Already the given background for Genesis Ray, I'll just briefly touch upon what was earlier discussed in case you have just joined in. So Genesis Ray is a technology and research company based in Singapore that develops cloud-based mapping and analytical solutions which help companies make better informed decisions in the renewable and clean energy sector. So today's knowledge series webinar is titled Fundamentals of Renewable Energy Resource Modeling. Uh, Before kind of diving into the details and moving ahead, I'll just briefly share with you my journey. Okay, before beginning the webinar, by fundamental training, I'm a mechanical engineer, but I always had deep connection and love with nature, which kind of made me a hiking enthusiast right from my early days in life. Right, so again, this was one of the primary motivations in my life, which made me take a transition from my own mechanical engineering domain to something like study atmospheric sciences and in particular climate modeling. So, I mean, this is a quote and one of the images which I just took in one of my hiking tours, which kind of says that if there is an option in life which excites you as well as scares you at the same time, you might try it. It might be a good thing to do. As we'll, talk about more about these things as we move along the talk. Now, before kind of moving ahead with the talk, I'll just, because I said I'll engage you guys. So I'll just try to understand that do you guys understand or know what is nature's blanket? Uh, I mean, you can post your answer in the chat box. It would be really interesting. What do you mean by nature's blanket? If anyone has heard about it, or if not, it's okay. Okay. So I'll just give you a blanket of nature, I mean, basically. So anything, what comes to your mind, you can type it over. Okay, good. So, okay, so next move on. Before
I'm so sorry. Is the chat box? Are you able to chat?
I could see the chat window, Raima, but I didn't see any comments from anyone.
Yeah.
So maybe I thought nobody dropped in a
Just give me a second.
message. Yeah.
Okay, just go ahead.
Sure. No problem. No issue. So if not, I mean, you can just think of that as you move along because I'll be shortly answering that thing.
Mm-hmm.
So, Raima, we may have the poll. So before kind of diving into the details of the webinar, let's have a poll question just to make kind of set things in perspective
Okay.
for the top one.
Okay.
Yep. So I'll just wait a minute so you guys can vote in your answers. Okay, cool. So, Raima, we may look at the poll results.
The polls, the answers are coming in, so just hang on a while because I'm seeing the numbers.
Sure. Okay.
Yeah.
Sure. No issues.
Just go ahead and. let you know when we hit the maximum number of people
Okay,
for
no problem.
trying to answer.
Yeah. We take our time. So it's the poll is basically, as an organization or as an individual, how often do you use resource and climate modeling for resource assessment, for a site selection or any other complex decision making process? So the four options are extensively, sometimes, rarely, or never.
Okay.
Okay, great. So we have a fair bit of audience who extensively use it. There are some who have never really used it, and there are a few on the on the later end of the window. So okay, so I hope by the end of this talk, the guys who fall in the window of never will be really excited to learn more about it and follow it. Okay, sure. So uh, to move along or to set the problem in perspective, here is a small one-dimensional model which I've just constructed, which kind of just tells about the balance of energy on our planet. Okay. Now this is something, a knowledge which was known to people even thousands of years ago. So I have taken a verse, a Sanskrit verse from one of our ancient literatures, which kind of says Aditya Jayate Vrishti, which basically says that sun is the supreme god. Okay. And why does it say so? So the reason is there is a typical nature's blanket which has been gifted by Mother Nature to us humans, which make the Earth's planet habitable. What do I mean by that? So here is a solar radiation from coming from sun, which kind of hits the surface. A part of it reflects back, but some part of it goes inside into the surface, which kind of heats up the surface. Now, in this universe, everything is balanced, right? What goes up comes down. So similarly, once this terrestrial system starts to get heated up, it starts to radiate its own energy. They are typically long wave radiation, and some of it is kind of trapped by the atmosphere, and which is radiated back to the ground, which ultimately is the blanket effect. So you can imagine on a cold winter night when you're sleeping, you often feel cold, right? So we often take a blanket. Does blanket has its own heat source? Not really, right? It kind of traps the heat energy which is emitted from our surface. So just in the very simple way, Mother Nature gifted us that blanket. Okay, and talking about it further, what's happening to the fate of that blanket? So as I talked about earlier, that everything is balanced. What comes in goes out. So on the left hand side on this graph, we have the natural greenhouse effect, that there are certain gases in the atmosphere which kind of help in radiation of the radiation from the atmosphere to the surface. But with time, due to the human-induced activities, we have seen an increase or enhancement in these certain compounds in the atmosphere, and the data speaks for itself. For example, on the right hand side, we have the consumption in different kind of fossil fuels, which our human activities use for example, electricity, heat, transportation. Okay, so the green one is the gas, the purple one is the oil, and the red one is the coal. Okay, so you can see right from about after the industrial revolution, there has been a steady rise in the consumption of these different fuels, to meet our increasing energy demand. The world was going through a fast industrial revolution. Okay, now similarly, now here is the data from different global meteorological agencies, namely NOAA from Japan, where we can see the temperature data is also plotted on the same axis, and which also kind of shows a similar increasing trend. So what's happening up, we made that blanket kind of thicker by adding or dumping in more of these gases because of the consumption of fuel and etc., to meet our growing energy demand, and which is ultimately leading to warming of the climate, okay, of the planet, basically the blanket which was gifted to us. So what's the solution to this blanket? Okay, uh, again, one of the solutions is renewable energy. That's the big solution to improve the blanket's health. Now over here is plotted data from the upper one is from nasa.gov. The lower one is error interim data, another reanalysis product. So on the top panel, we have solar radiation. So you can imagine this graph as the color scale, which runs from blue to red. So regions which are red have a higher amount of solar radiation on the surface, which gets on the surface, whereas the ones with bluer or yellow have relatively lower numbers. Okay, so you can see there is a kind of a very pattern of solar radiation, and something similar is also can be observed for winds. So on that account, I'll just try to tell you a number. For example, if we tap the total amount of solar energy, the solar irradiation, that would be amount to approximately 600 petawatt hours per year, which is approximately, peta is 10 to the power 15, and it's equivalent to a quadrillion of watts. And however, the global consumption is only 140 petawatt hour per year. So we already have a surplus kind of a thing, but which could be a big solution. Okay, but adding to that, I mean, just couple of fact checks that the United Nations has said that access to clean energy is one of the sustainable development goals. Okay, in addition to that, there is a quick data that if we just invest 1% more on clean energy, it can help us avoid the worst of this global warming and other climate change effects by approximately 80%. Okay, so but again, easier said than done. Everything comes with two coins actually, so it has its own sets of challenges. So here are some of the challenges in effectively utilizing renewable energy. Number one, that's temporal variability. What does it mean? That the renewable energy plants which produce energy, they only work when the sun is shining and when the wind is blowing. So they have a strong temporal variability. They also have some kind of an uncertainty, because we need to know ahead in time. I mean, we need to predict it. Similarly, like temporal or time variability, we also have a spatial variability. We looked in the previous chart, there were certain regions which were having a higher kind of a solar energy potential. There were regions which were on the lower strata, right? So that adds to the spatial variability. In addition to that, there is location specificity. What does that mean? That there could be a location where I have a strong source. Okay, imagine one of those red areas in the previous chart which I had shown, but not necessarily there could be a transmission infrastructure at that point. Okay, so that makes it location specificity, the next challenge. And finally, adding to all of this, we need an access to real-time, long-term accurate information, okay, which is at high resolution, to kind of support greater penetration of resources. It is important to kind of have a understanding of the long-term record and quantify this intermittency and volatility. So one needs such kind of a data set which can help us tackle this challenge. So that access is another challenge. Now, just diving bit more into the details, that what's basically driving this uncertainty. What's basically there's a chat which says that thanks for leaving the chat. Okay. Good. So again, I'll make the session interactive. Thanks for that, Raim. I'll ensure that we have more kind of discussions. Okay. So why not? Let's do it right away. Okay. So as I talked about, let's kind of think in very simple terms that what could be the factors, for example, if we talk about wind, which could be, have a strong role to play in its intermittency, which could make wind variable. We all understand that. Just think as a very simple guy, you are standing somewhere. What could be the factors which could affect kind of wind potential at any region, or the wind speeds in very simple terms? Anybody? Can we have your ideas just dropped in the chat box? Topography, great. Amazing. Yeah, I mean, on a mountain.
Can you repeat the question again, Abhishek?
Yeah, sure.
Can you repeat the question again?
Yeah, sure. So the question is, if you are at any particular location, and as you know, we talked about the intermittency in the previous slide. So what could be the variable factors or factors which cause variability in wind speed? Okay. Just think, I mean, you understand wind, right? You have been to different places on the globe, for example, where you have sensed more wind. What was the driving factor and all? You can just drop your thoughts in the chat box. One of the points is topography, which is very accurate, right? For example, if you are on a hill station or somewhere where you have a higher altitude, so there could be a higher wind speed at that point, or you are closer to the surface at that time, you could have a lower wind speed. Any other parameter you think? Anybody? Surrounding features?
Abhishek, there is something in the Q&A saying pressure difference in atmosphere.
Oh, great. Amazing. Actually, that's the main thing which drives the wind. So that's the most important point. I mean, so on that
Pressure,
point,
yeah.
if we look at this slide, okay, so when I talk about factors influencing resource numbers, so I've written three keywords: local scale, regional scale, and global scale. So what makes this process more complex is there are different processes which are interplaying at different scales or space and time. For example, pressure system, large scale pressure system, which can have a mesoscale in meteorological terms, kind of a scale which is affecting your wind. Okay, then you could have a sudden area where there is more roughness, okay, which can again reduce your wind shear. Okay, so that's a local kind of a scale thing. And in addition to that, supposedly, as earlier discussed, at a higher topography or at a, you're close to the sea or sea surface, then you might have a different kind of a wind profile. Okay, so yeah, thanks for that. The different points which came up through the chat, but it just helps me illustrate the point that the process is complex, right? And there is interplay of these different things. Now, to understand that this thing, I mean, to better kind of predict what could be the resource numbers, the entire edifice of atmospheric science rests on three pillars. Okay, the first one is the climate modeling. I'll talk about it in much greater detail in next slides as we move along. Second could be of standing weather station, where we have these different sensors installed, and they are measuring, for example, pyranometer. It measures the solar radiation. Okay, for instance, there could be a wind anemometer at a particular location. But again, we have satellites which kind of sense remotely, and then through different mathematical approaches, we are able to compute what could be the solar radiation at particular location. For example, let's just keep it simple. But again, if we talk about each of these different pillars, they all have their own limitations and they all have their own advantages. For example, installing a weather station cannot be done continuously, right? We cannot have a weather station at every point on the globe, which undoubtedly is the most accurate way, but still it won't be practically feasible to have a measurement at each and every grid point. Secondly, satellites. Satellites are sensing, the Earth's surface as it revolves around it. But supposedly in between there is a cloud, okay, and the satellite becomes blind. So that's another kind of a disadvantage. So in principle, the reality or the real picture lies at the interface of all these three pillars. And at Genesis Ray, we just do that. I'll talk about it more in detail as we move along. Okay. So as we talked about the climate modeling is one of the effective solutions, which can help in effectively utilizing renewable energy source by accurately, modeling climate and weather modeling. But again, always remember it rests on the edifice of all the three pillars, not just one. So here is uh, a climate simulation basically for one full year. On the top, we have the timestamp where you can see how there is different kind of weather systems which are just getting transmitted in one part of the globe to the other. Okay, so this is kind of in the early season of January, where if we talk about the global circulation pattern, there is something called as for all the meteorological folks out there, ITCZ, right, the intertropical convergence zone. So okay, so it's something over here at this point where we can see there is convergence of the trade winds. Okay, similarly, you can have a simulation where you can see sea salt, that the blue things, and the red is the dust is getting transported. So you can have chemical transport models which are trying to emulate what could be the changing pattern in these different particulate matters and sea salt, etc. Okay, and then number third, my favorite is as this kind of a weather or a hazard prediction using different scales of modeling. So again, a couple of days back, we had a cyclone warning again over southern India. So here is a map basically which illustrating the cyclonic vorticity over southern India. You can see there was a cyclone formation which ultimately ended up as a depression. Okay, so this is again an output from ECMWF. So again, once we are able to model these processes, provided they're accurate, that can really help us solve the problem of effective utilization. Okay. Now, again, just visiting some more fundamentals. What we are looking at previous slides are fundamentally charts and animations, right? But at the base, at the fundamental level, there are certain equations which are just being modeled. And these equations are called as primitive equations, which basically tell how the atmosphere, what equations govern the evolution of atmosphere both in space and time. In principle, there are six. I'm not diving into the details of them, but you can just imagine inside a computer model is fundamentally inside a computer, you have these a virtual earth with these different grid systems on which all these equations are solved. Okay, talking about terminologies, there are two broad kind of modeling systems. One is global climate modeling, the other is regional climate modeling. Okay, when I talk about global climate modeling, I'm typically as suggested by name, I'm trying to model the entire globe. And if I'm doing for a region, so it would be again powered by the GCM, but it would be kind of simulated over a smaller kind of a domain. Everyone has their own advantage and disadvantage. For example, the GCM will, because we have to cover the entire globe, so it will come at a coarse resolution. What do I mean? Resolution is the size of one such grid box. Okay. Now, the moment I'm covering a smaller area, I can have a higher resolution. That is, I can have a higher grid size. Okay, so which makes the GCM process a bit computationally expensive, whereas RCM is computationally more efficient. On the example front, there are certain reanalysis products, for example, MERA2, ERA5. I'll talk about a bit about them in the further slides. And for regional climate modeling, we have models like WRF modeling system and Cosmos. Okay, again, I'll talk about it as we move along. I mean, in principle, to sum it up, there are different scales of modeling, global and regional. Okay, so at Genesis Ray, this is the entire climate or weather modeling pipeline. How do we go ahead with it? So, I mean, if you look, this is visible that the pyramid, our pyramid, atmospheric modeling pyramid rests on three pillars. That is climate model, satellite data, and ground observation. So we take different kind of global data sets. We kind of validate them with ground-based observations to kind of identify which is the best kind of different products are available. So you need to identify which is best, depending on your region of modeling. And then we perform different pre-processing through different packages and softwares to ultimately come up with a model performance report at the initial stage. Now, once that is done, then this entire modeling pipeline bifurcates into two different regimes. The one goes along with dynamic downscaling, that is WRF modeling system, in simple terms, weather research and forecasting modeling system. And the other one is the statistical modeling system. Again, I mean, the crux of everything is at the end of the process, you always need to come up with the model performance report, which basically talks about how good or how accurate your numbers are. As I told, these are just numbers, but you've got to make sense that numbers are, they're talking sense. They're making, they're logically correct. Okay. So some more technical details, starting from the WRF modeling system, there would be folks, I hope, in the audience who extensively use WRF modeling. So going by the technical jargon, WRF, the weather research and forecasting model, is a next generation mesoscale numerical weather prediction system, which is often used both for operational purposes like forecasting tomorrow's weather, as well as for atmospheric research purpose. At Genesis Ray, we are utilizing it both for reanalysis, that is studying a past event, as well as for weather forecasting purposes. Now, provided, as I said, weather forecasting in terms of mathematical modeling is an initial condition or initial value problem. Okay, so in that case, the initial condition or the data sets which drive your model should be very accurate. So here is just an overview of kind of data sets we use. While forecasting, we are using the the GFS product for our reanalysis purposes. This is something unique over South Asia. We are the first one to kind of ingested ERA 5 data inside WRF model, which I'll show about the impact on the results. Apart from that, the DEM data which is used in the model is at a kilometer resolution from USGS. The land use data is from MODIS. And for forecasting system, we use the GFS dataset. Okay, this is an overview of the data sets we use. Now, again, very important tool is, for forecasting is the WRF data assimilation system. So I talked about that it's an initial value problem in case of mathematical modeling. What do I mean? That the present time from where you start the forecast, that is at time t equal to 0, it has to be the most accurate one. So the 4D war technique is fundamentally based on that principle. So if you look on the upper chart, so here you have a forecast, which can be seen through this animation, where we come up with an initial forecast, and then as we move along in time, we kind of get different observations. Okay, and then in the small assimilation window, when we have these observations available, data sets available, primarily these are satellite data sets. I mean, some of them are listed in the slide. We incorporate them at our initial condition. And then here is the red one, which kind of you can see is improves the forecast, okay, which is much closer to the observation. So again, to sum it up, 4D war data assimilation system ingests real-time observation from multiple observation platforms, mainly satellite, I'll say, and it's assimilated in that window to improve the forecast. Okay, I hope it kind of makes sense. Cool. So remember the two bifurcations, the one which went through with the dynamic downscaling, I briefly discussed in the couple of slides. Now I'll just briefly talk about the statistical modeling part, okay? And then if it's kind of becoming monotonous, so soon I'll be having a kind of a question exercise for everyone in next slide, okay? So if we talk about the statistical modeling, one of the very important techniques or tools is the bias correction. Now, in terms of, if we talk about in very simple terms, what is bias correction is you make an estimate. For example, I say that tomorrow's or not tomorrow's, few hours from now, this is how things are going to be, okay, but you find out it's not that, okay, so you correct that, okay, you correct the estimated thing, and that's what is called as the bias, and the process is called as the bias correction. So in this slide, fundamentally you have you can see the data has been interpolated. I mean, again, one of the studies from our from Genesis Ray, where we have interpolated the data at a higher resolution, and you can see how moving from 36 to 4 kilometers kind of helps improving the numbers in comparison to the observation. Okay, and once we have that thing, the 4-kilometer product and the observation, we kind of perform a bias correction on the different points. And on the right hand side, I have just two kind of illustrations of the product. The top one is showing the wind speed vector over the modeling domain. This is somewhere in South India, which has been bias corrected. The plot basically shows wind vectors overlaid on a pressure type spatial resolution. And the bottom one is basically the GHI thing. In renewable energy, GHI is global horizontal irradiation. In very simple and layman's term, what does GHI means is at a surface, if I have a surface, a horizontal surface on the ground, so what is the total amount of solar radiation in the short wave window, which kind of irradiates the surface? Okay, that's what is GHI, global horizontal irradiance, GHI. In units is watts per meter square. So, okay, now I have a quick quiz where we all can kind of share our thoughts. So this is a new kind of a modeling system which we are trying to develop at Genesis Ray. This is, I'll say, a ML or a machine learning based algorithm. So here we are trying to predict in time how is your solar radiation or GHI changing. Okay, so for example, we all know about the artificial intelligence, right? Today we have all these algorithms while ordering a food or ordering a product, which kind of tells you based on your kind of likes and dislikes what kind of product is best suited for you. Okay, but there is something called as natural intelligence. Okay, so just if you can, guys can just type if you are at a location, okay, solar radiation. I'm just trying to compute or try to understand what could be the solar radiation at any particular location. So what could be the factors which would be playing role? Okay, can you just type it out? I hope the question is clear. That if I have to just imagine, you need to compute solar radiation, just the raw number. Okay, so what could be the factors which would be playing role, like we did the exercise for wind? So what could be the factors which could be playing in for solar radiation? If you can just type your answers in the chat box. Clouds, yeah, great, absolutely. Cloud cover, atmospheric makeup, including gases like CO2, of course, and other emissions can vary greatly. Latitude, terrain, particulate matter, amazing, aerosols and clouds. Yep, perfect. So again, thank you so much for your views. I mean, you guys already know it. Okay, so this is the kind of the ML based natural intelligence model, I'll say, where we kind of based on long-term data sets, we kind of understand and develop relationships between different parameters, and then we try to predict what's basically driving your solar radiation. So in case of solar radiation, the top one is basically I'm showing Earth. Okay, so rotation. So which position you are at different times of the day, has a different kind of a solar radiation. For example, we know that, right? It could be late evening in the United States of America. People who have joined in from there, and it's daytime in India and late afternoon in Singapore. So that's something, a function of zenith angle in technological jargon. Number two, aerosols. Someone rightly kind of pointed out in the chat box that if there is aerosol, there could be aerosol dimming at the surface, that some amount of solar radiation gets scattered back. And of course, clouds, right? If there is cloud, we don't see the sun, okay? So we kind of develop long-term data sets. So it's ML algorithm is fundamentally driven by long-term records, okay? But again, things can go wrong. In that case, here comes the last and the final thing, where you can see the animation on the right-hand side, where we train the data set based on the observation. But that's the most important aspect of any of these algorithms. The observation, always remember, the most important pillar is the observation. So we have to always utilize that in all our numbers, okay? So I hope we are ready for next poll, Raima. Maybe we can have the question.
This is poll number 2, right?
Yeah.
Okay.
Yeah, so the question goes around like we looked at some of these processes, right? Climate modeling. We talked about some statistical techniques, bias correction, downscaling. So do you think this can help us plan a renewable energy project better? There's the 4 options. You may vote for the one you like. So we have the numbers right.
Okay.
Okay, cool. So thanks. That kind of motivates me. It's worth the investment in time. Some of you think it's challenging, and there is certain section you feel I'm not sure. Okay, so my next couple of slides are for you. That what would be the advantage we get with this? Okay, I'll share some real world examples actually through the data sets developed at Genesis 3. Okay, so here's the first kind of again, the data sets which has been developed. So on the left hand side, you can see this again GHI. Remember the global horizontal irradiation. It is, we identified at Genesis Ray Era 5, one of the latest reanalysis product from ECMWF is the new champion of renewable energy modeling. Okay, and so the raw data is approximately at 27 kilometers. So which is plotted over here on the extreme left window, and then it has been downscaled using different statistical methods at 1 kilometer resolution. Now, in addition to that, if you remember the challenge, the volatility, where we talk about the intermittency in the renewable energy source, so our kind of product, it provides a statistical level of confidence by, it computes different percentiles and exceedance probabilities, okay, at every of these locations for a long-term climate record. Okay, after making an accurate data, we kind of come up with these estimates, which can really help you plan your project way ahead in time. Okay. In addition to that, uh, yep, sorry. So here is another example, real world example of bias correction. So on the right hand side, if you look at the top window, so here's a wind speed without bias correction, where the blue kind of markers correspond to the measured wind speed at any particular location, and the orange one, which is on the same graph, it kind of depicts the simulated one. So initially we can see there's a large discrepancy. I mean, there is we can see we are not able to accurately represent the numbers. So again, we apply the bias correction. There are multiple methods of doing that. Uh, I'm not doing the details, but supposedly we select one of the methods called as quantile mapping, okay? And then we kind of correct the data. Here you can see it kind of gets mapped accurately. Now on the left-hand side, I've plotted the same data on a XY graph, okay? Just to show or to illustrate the kind of increase in the linear model fit. So on the top panel, we have the before data set when there was no bias correction involved. So this blue line, if I fit it through, the regression slope comes out to be approximately zero point 0.2. Whereas now, after doing the bias correction, I'm able to better represent the numbers on the ground where the slope is close to 1. Okay, so that's the kind of strength which bias correction gives. I mean, improves your accuracy by a significant amount. Okay, similarly, as I talked about earlier, the WRF modeling system. Okay, so at Genesis Ray, we have kind of developed high resolution forecast and reanalysis products for WRF modeling, where we kind of divide the entire uh, domain into different high resolution kind of subdomains. And I'll just zoomed out one of them for quickly showing you the impact of ingesting ERA 5 data. Again, I'm saying that we are the first one to have ingested ERA 5 data into WRF modeling system over South Asia. You can see the top panel shows you the terrain height, like the orography thing. And here is an XY graph over Kannur, one of the locations, the coastal side in South India. You can see the R square value is approximately 0.96 in the month of monsoon, now, which I mean falls out there who are in meteorological modeling. An accuracy of 96% during monsoon season is quite great, actually, right? You would appreciate that. Similarly, it's often said modeling wind is the biggest task on the planet. So similarly, you can see, incorporating ERA 5 data set, here is another profile. The box is again showing the percentile. Remember the 10th, 90th, 50th, 75th percentile of the measured and the WRF wind. You can see how accurately we are able to even represent the diurnal pattern. I mean, how at each hour the wind is changing for that particular monsoon season over Kayathar. Okay, so that's the strength basically it gives back. Okay, so with that, I'm kind of trying to reach. I'm now end of my talk, where I'll just say that I talked about the complicated processes, right, which we do at Genesis Ray to ultimately improve the accuracy, which will help you take informed decisions by our climate data sets. So we give you ready to use climate data and resource potential values. As I said, there are different reanalysis products, different kind of modeling systems. So we kind of harmonize them to the same grid, perform statistical corrections like bias correction, and we give you a fast access to the data sets. Okay. Now we take care of all the hassle in simple and easy terms. And at the end, all these data sets end up in products. Some products, like for example, Resource Pro. Okay, so we have a suite of products, as I discussed before. I mean, these ends as a product. So I'm one of the key persons who is involved with my climate modeling team for Resource Pro, which is basically development of an accurate historical resource data set that can be used again to estimate accurate solar and wind data at any location. Okay? Apart from that, as I said, we have other, in addition to that, we have other suite of products which you can go through as it has been listed in the slide. But it's important to mention the pioneering thing. Okay, so everything started from Genre Explorer. Okay, so it's something like a Google Earth kind of a product where you can visualize the location or infrastructure of different solar and wind farms. To be honest, it's an amazing tool. And for especially for developers and researchers who want to study different locations and how they are developing in the renewable energy sector. Okay, and apart from that, there are different products, including Market Pro, Valve Pro, company and country reports, which would be Site Pro, which are lined up for launch in early 2021 and mid 2021. And I hope that, by that time we have a COVID-free world. Okay? So on that note, let's go for the next and the final poll of the webinar. Yeah, Rahima, we may have the poll question. Okay, so Rahima, we may have a look at the numbers. It's done.
People are still answering. Abhishek.
Okay, sure, no problem.
I'm still waiting for.
Yeah.
Yeah. Give me a moment. Okay. All right. Okay, I'll end now.
Yep.
Ta-da!
Okay, great. So you need more information? Sure. I mean, you can get in touch with us for more information for sure. Okay. So with that, I kind of come to the end of the webinar. But again, I'll just highlight upon the summary and the take-home message from the webinar. Okay, so always remember, where do we started? We looked at the nature's blanket and fate. So that's the big picture, right? And investing in renewable energy is the big thing. It can improve that blanket's health. Then we talked about the different challenges like intermittency, volatility, specificity. Which kind of is the major challenge or hurdle. For effective utilization of renewable energy, and how climate and weather modeling, accurate climate and weather modeling can help us in effective utilization. And remember the three pillars, right, for the vital solution. Our team has identified ERA 5 model as, model product as the new champion of renewable energy modeling. And, we provide you a one-stop solution to all the challenges, associated with RE and its utilization. So to sum it up, to save the earth, we need RE, that is renewable energy. But for better and effective utilization of renewable energy, we need accurate climate and weather modeling. Okay. So on that note, I thank everyone for your time. Thanks to my colleagues and climate modeling team. And thanks to Rahima and the BD team. Thank you so much. You may, yeah, just. Rahima, it's not audible actually.
All right. Okay, no problem. Okay. So thank you so much, Dr. Abhishek, for the very insightful take on this topic. Now is our Q&A time. So please feel free to drop your questions in the Q&A chat box, a Q&A box, and then we will address them. Okay, so let's see what questions you have. we will try to finish this by 4 p.m. But if it does get extended by the question, we'll ask you one more time. So please feel free to drop your questions in the Q&A box. Right. Yes, there will be the recorded video of this webinar. So there is a question here. How can renewable energy resource modeling help in reducing investment risk associated with new projects?
Hi, Rahima. I think I can take that question.
Okay.
So, like any project, renewable energy project can be having different uncertainties and investment risk, like a construction-related risk, policy or price-related risk, and but more importantly, related to resource or energy risk and the operational risk. So the climate modeling or resource modeling comes into rescue the to the need of risk mitigation of the energy or operation related risk. So one of the main aspects of investing into a project by estimating its internal rate of return, NPV, etc., various financial indicators. And to do that, we need to accurately predict the amount of energy we will be able to produce by that project, and eventually we'll be able to sell that energy in the grid or market. So with respect to that, I think accurate resource modeling helps us to uh, help provide various informed numbers related to various particular location related to the project. So in terms of renewable resources, as we have variability and uncertainty, we often quantify from long-term historical records some exceedance numbers in terms of probability, like P50, P90, etc., which actually states that how much the actual wind speed or wind generation will be exceeded by that percentage of probability. So with that kind of a number, investor can calculate what will be its expected rate of return or payback period that he can take into account before investing. But and in addition to that, related to operational risk, I think when a particular project is connected to the grid or market, whether they'll be able to sell all the energy to the market depending on the transmission congestion and other aspects of the system. There we have to again check whether our renewable energy generation is able to induce or kind of integrate into the grid properly. So in that case also we need good resource number. So both the for the both the aspects we need good energy resource modeling activities.
Okay, that's great. Thank you so much, Dr. Partha. There is another question here. How does renewable energy resource modeling, how is it important for power sector infrastructure planning? I think Vishnu, you'll take this.
Yeah,
question.
Rema, I think I can answer this question. So, so before, of course, I give the answer for this question, let me just start with a scenario where there is no, let's say, modeling exercise happening. Let's say if you have a particular site, first look for, let's say, the data. For example, let's say we just go for, let's say, RE data in terms of solar irradiance or let's say the wind speed. So from where we get the data? I'll just hold on for a second. There is some disturbance happening. Just a minute. Yeah, sorry. I think there was small disturbance. Yeah. So basically, talking about, let's say, the data where we get, let's say, the solar irradiance or the wind speed. So there are a few sources that we look for. First is, let's say, the ground weather station data. Of course, that's the most accurate data that people look for because, but the disadvantage with that particular data is it's not available for a, let's say, historical kind of a thing for the public. At the same time, these are all location specific information. information in terms of, let's say, the weather stations are concerned. Second thing is the satellite data, as Abhishek was also mentioning. Of course, they have historical level of information, certain providers, but again, they lack in, let's say, the resolution. We talk about they comes with pretty low resolution kind of a thing. And of course, there are many other data providers or which they comes up with an average number. Maybe they don't consider the seasonality or the changes in the climate. So what happens there is actually there's a high probability to get, let's say, a wrong estimations of resource profile, so that if you want to calculate an energy yield assessment or something, that can actually go wrong, the entire analysis. So the entire point is, if we have a weather research forecast kind of a modeling happening, and of course some doing some kind of a post processing maybe for the data for past 10 or 15 years, actually we'll have an hourly weather information for a set resolution, maybe for a 10 kilometer or 5 kilometer, depends on the user, whoever it is. So that hourly data can actually is a very key aspect to understand, of course, the volatility as well. At the same time, if we can actually further reanalyze that by cataloging these hourly information into percentiles. So percentiles, that everybody might be aware of it. It's a statistical level of confidence. So normally we use P50. Of course, we have P75, P90 kind of an analysis. So that what happens there is, of course, depends on the client segments that Partha was also mentioning. So they can actually select any of the, let's say, P50, P70 kind of an analysis, and they can actually calculate those yield outputs. Maybe everything ends up in a financial aspect as well. Those lot of analysis can be done if we have the accurate kind of a resource modeling exercise. Then it's pretty easy to put a power infrastructure or a particular project in that specified location itself. So I think it's very vital to have these models running, rather than relying on the other set of information that I was talking about.
Okay, thank you so much, Vishnu. There is a question by Akshay on the prediction of WPD in the scope of Genesis Ray. How does it fare in comparison to the various wind atlas maps available? Any of the panelists or speakers who want to answer this?
Sure, I'll go ahead with it. Then maybe
Okay.
Abhishek can add on that. So again, as you talked about, it is in the scope, of course, both long-term reanalysis development, that is development of past data, as well as forecasting. Now, in comparison to fare with wind atlas map, maybe Anushika can better comment on that. But as far as I'm concerned, I look with the ground-based observation. For me, that's the most accurate thing. I don't believe in any other product. So, and as I showed you in one of the slides, right, we were able to accurately represent the numbers, which was there from a weather station at 10 meters in southern India during monsoon season, which is one of the most difficult months to simulate over the Asian continent. Okay.
Okay.
Yeah, that was
So
the point fundamentally.
All right. Anushika, would you like to continue from there? Or
Yeah, so basically, what
would you
Abhishek
like to take
just
the
mentioned,
okay.
I would just, add some points to that. Given the solar atlas and the wind atlas that's freely available, they just give you a mean, a long-term average. Weather has changed particularly, very abruptly over the last decade. So, considering just a mean to decide, of course, you can figure out what is a relatively good, resource location, but how good that resource location is and how far that resource location will actually produce, optimum power is something that you have to focus on, getting to the nitty gritties of the minute wise weather information. So if I just consider a mean, it's good enough to show on a map that, okay, south is better than west or east is better than north. But, for real power development, for real time generation of power, if you really need your numbers, then probably, modeling it and getting it, cataloging it into the percentile information is a better deal, because of course you would like to know how good a area can produce power over a longer period of time, not just one particular mean which actually addresses the wrong information given any kind of hazard condition or any kind of cyclonic weather condition. It just shifts your mean. The mean shifts the actual idea of what you can actually expect from the location. So it is better to look at an overall picture rather than just looking at a particular mean. So yeah.
Okay. Thank you, Dr. Anushika. We have one last question. If you could just wrap that last one question in a minute. What is the ideal spatial and temporal resolution of weather data to be used for the identification of suitable sites? If you could just answer that in 1 minute, we can close the webinar. Just nice.
Okay, so Rahima, I'll take that. It's in relation to what I've just mentioned is, so it basically depends again on the stage of the analysis. Now, if it's in a very preliminary stage, a coarser resolution is good enough. So for example, an hourly weather data, just trying to find out the relativity of resource availability across the landscape is good enough. But when you're in the detailed planning stage, when you have almost decided on your specific site, when you have the exact coordinates you're talking about, you need to incorporate more variability to estimate the real-time power generation. So minute-wise weather information is suitable for this purpose. Now, as far as spatial resolution is concerned, it again varies according to the geography under consideration. For a larger geography, where the objective remains to broadly check the resource availability across the region, you can opt for a 10 kilometer, a 5 kilometer, of course, keeping computational feasibility in mind. But similarly, when you have 2-3 shortlisted sites and you're really trying to make a decision between your 2-3 sites, then the ideal resolution would be 1 kilometer or less. This is the resolution of project development. So, but beware that this is a highly computational expensive task, even for a very small fragment of land. So if you ask me for a typical site assessment exercise, immediately before installation, I would go with the rule of thumb where the spatial resolution should be 100 meters and the temporal resolution should be 1 minute. So yeah, that would be my answer.
Okay, there is one more question that just come in. So do you want to take that? That's by Akshay. The weather observations are not available at the location. Which atlas or alternates does Genesis use or recommend during preliminary stages for power development? Say, yeah.
Sorry, Rahima, I could not understand the initial part of the question.
If the weather observations are not available at the location, which atlas or alternates does Genesis use or recommend during preliminary stages for power development?
Okay, so like I mentioned, we kind of generate our own resource models in-house. So we don't really depend on weather information from the ground as such for every location. We kind of generate it seamlessly for the entire geography, and for wherever there is ground weather observations, we try to validate our own resource models and bias correct it just in case there is a bias correction is needed. And therefore we go ahead with using our in-house created resource models. Abhishek, if you would like to add something to this.
Yeah, of course. I mean, the most of the things are already covered in the answer. It's just that it could be, for example, you don't have a weather station. For example, if you're planning something, high up into the mountains, just giving a random example. So in that case, you would have to rely on some kind of a satellite data estimate, which can help you somewhat perform a bias correction at a bigger spatial coverage, in case there is no availability of any ground weather station data. So then our models have to be calibrated using satellite data. And again, one has to be very critical with using satellite data. As I said, everything comes with 2 sides. So we'll have to, for example, perform a cloud filtering algorithm or something along those lines. Hope that answers your question.
Okay. All right. I believe we have come to the end of our webinar, and we are truly appreciative of your presence. This webinar is recorded, and we will send to you the recording. If you need to reach us and ask more questions, we'll be delighted to we will be delighted to answer some of your queries. You can email us at contact@genesisray.com. We have a survey right after this webinar, and where you can request for certificate and materials. We will be grateful if you can complete the survey. There's about 9 questions in there. So thank you very much, and till we meet again next month for the next knowledge series webinar organized by Genesis Ray. Thank you so much, all panelists and speaker. Okay,
you,
so
everyone.
say
Thanks,
goodbye
thanks,
for
everyone.
now. Okay,
Thank you,
bye-bye.
everyone.